once again at the physics video lecture. Physics 107B, video lecture 12. So I had a question about one of the homework problems, the spinning shell, spherical shell of charge. And it's such a good problem, we should have actually talked about it at length. So today, instead of continuing with the waves, we're going to look at that problem, chapter 8, number 17. Okay. The spherical shell, and then it's used to model an electron. It's a very interesting problem. It's a rich problem, has all kinds of content. So let's go ahead and jump right in. We've got the spinning spherical shell. So of radius r, radius capital R. We're gonna have to make use of everything. So let's set this thing up, and the idea will be that it's centered on the origin. We'll be making use of spherical polar coordinates. So we'll have our shell here. And if we're, at some point, our spherical polar coordinate, well, we'll draw them in as we need it. Okay. Right now what we have is that it's covered with charge. So surface charge density is an electron charge over 4 pi radius squared. It's rotating with angular speed omega. And there are electric fields, of course, due to that charge distribution. There are magnetic fields due to the charge distribution. We have to calculate all of those things. So there's a radius r right here. Okay, we had in chapter 8 the fact that the field carries energy, it carries linear momentum, it carries angular momentum. So this is our chance to actually calculate all these things in a really important example. So let me go ahead and set some of these expressions up. I'll probably have to write them down more than once. So let's see, spherical shell radius r, surface charge. Good. So the electromagnetic field carries, like I said, energy, so there's going to be an energy density, carries linear momentum, carries angular momentum. So energy, and we had an energy density 1/2 epsilon naught electric field squared plus 1 over mu naught magnetic field squared. We had linear momentum. And that was just with the pointing vector. So I'll use the nomen, well, I had written it with this cursive electromagnetic momentum density. We're calling that G in the text, and it's just epsilon naught E cross B. Okay. So there's our pointing vector to a constant factor. And directly under here, it's going to carry angular momentum. letter am I giving that? L, electromagnetic angular momentum. But this is the density, is just R cross P, or R cross G, so it's R cross epsilon naught E cross P. And the total of these things, these are densities, so the total energy, linear momentum, angular momentum would be the integrals over space. So total energy for example, for the electric integral U E volume all of space. Okay. And the same thing for the linear momentum and the angular momentum. Actually, for our spinning charge here, we're going to find that this integral vanishes, as one might guess, but these two do not vanish. So we're going to calculate those. See what else we have here. So yeah, the program I should outline is to find the electric field, find the B field, get this expression, do the integral, okay? Find the momentum, linear momentum density, calculate this, and we'll see, we'll actually be able to see from its form that it's not going to integrate, it's going to integrate up to 0, but the angular momentum density, which we'll find with this expression, will then also be integrated over all of space, and so we'll have the energy and angular momentum associated with the fields produced by this charged sphere. Okay, the electric fields will be very easy to obtain. The magnetic fields we have to do quite a bit of work because the rotation produces a current effectively, and it's the current that we integrate up to get the vector potential, and from the vector potential we get the B field. So yeah, there's a bit to do here. So yeah, outline, let me just outline what we are going to do so we remember. So we're going to find E, and it's one of those situations where the electric field and the magnetic field are different inside and outside. So we'll have to find E to find the magnetic field, 3, calculate total energy, electric plus magnetic field, which will be the total integral over this expression here. And then having these fields, we can calculate G equals epsilon naught E cross B. And we'll see at that point that the integral of this vanishes, that's fine. And then calculate L. In fact, we'll say this, L, use the uppercase for the total, that will be the integral of this vector L, electromagnetic D volume over all of space as well. So having found all of these things, that's a good exercise. What we're then going to do is discuss this as the model of an electron, okay? So we'll just say electron model. And the thing about the electron model is we want to compare the energy to the relativistic mass energy formula. So we're going to compare, we're going to actually equate, what do I have it here? This energy equals mass of the electron c squared. And we're going to compare the total angular momentum to the spin of the electron, which would be h bar over 2. So we're equating these two expressions in order to get some information about how fast is it spinning, how big is it. And so this model situation allows us to ran out of room, but I'm going to write it here anyway. 7, calculate R sub electron and V equals omega R. In fact, well, that's just an interpretation, of course. V is omega R, but we're actually going to calculate these two quantities, R and omega R, and see if they make sense. So this is an important exercise to try to model an electron as a spinning shell of charge and see whether the size and these speeds make any sense. Break the suspense right now. They're not satisfactory, but it's still an amazing exercise. Okay, so that's the program, and we'll just get started. I'll just leave everything, I'll leave that picture up there for a while, potentially, and then we can collect some more formulas. Good, so first of all, we have to find the electric field. Yeah. Find the electric field. Actually, how about I leave that list up there for the moment. Have everything up there at once. Of course, the electric field is pretty basic. That's just using Gauss's law. And so we can just write it down. So, electric field. So again, we've got drawn slightly smaller now. This object here centered on the origin, and from, just to remind us, E dot dA equals Q over epsilon naught, and the symmetry that we have, we've done this before, so we will say E is equal to here we go. 0 inside. Remember, all the charge is out on the surface of the shell. So R less than capital R. And outside, of course, is the famous result that for R greater than the radius, it's just looking like a point charge to us. So the field of point charge outside. So that would be E over 4 pi epsilon naught R squared R hat for R greater capital R. Just the field of a point charge. Good, so that's all we need to know for the electric field, I think. Yeah. So next, we're looking for the magnetic field. Now, the magnetic field is going to come as the curl of a vector potential. And the vector potential is just like 3 integrals of a scalar potential. So, where A is equal to, what's our vector there? Mu naught over 4 pi. mu naught over 4 pi integral j d tau over r minus r prime. So d tau prime, j would be a function of, r prime as well, okay? Because we're integrating over primes, and this is the position out there in space, so a of r. And this is back in chapter 5. So we don't have a volume, so actually instead of J equals rho times V, we're going to have a surface charge density. So this integral actually will be written mu naught over 4 pi integral, they use this new letter K, d area prime over r minus r prime. And we have this K is equal to sigma V, right? It's that rotating shell there. Just have a rotation here of the shell. And this V here, because it's a rotating object, we have V is equal to vector omega cross R, and it's R prime because we're on the shell. So that's what gets integrated, and that's been done in the book. So just having written this up here, I'll go ahead and give the results. Yeah. And just for the record, of course, this sigma, we had it up there already. It's E over 4 pi radius squared. Charge per surface area of a sphere. And this thing is rotating, so, these are the currents that are being integrated over. And so it's no surprise that the integral here is only going to be proportional to phi hat when we go into spherical polar coordinates, which is what, of course, we're going to do. This is already good for spherical polar coordinates. So yeah, it's no surprise that that integral gives you something proportional to phi hat. So let's continue right under here. So for our vector potential, we obtain A, and we'll just write this down. We get inside and outside, so we have mu naught or omega sigma over 3 or sine theta phi hat, and mu naught, mu naught r to the 4th omega sigma again over 3 sine theta divided by r squared phi hat again, and this one is outside and this one is inside, and in fact they're equal when r is equal to the radius. Yeah, it couldn't have been any other way in terms of the direction of this thing. In fact, this r sine theta omega r sine theta just shows us that it's a sort of a rotating bucket situation, even though we're on a surface, okay? Which means that the curl of this inside part, based on this form, you can already see the curl is going to be uniform inside the sphere. Outside the sphere, it won't be. Good, so I gotta make sure I have those down correctly. Sigma, R sine phi hat, yeah. Good. So what's the next step? We have to find, we're still on 2, I guess. We have to now take the curl of A is going to be what we're actually looking for, the magnetic field. So the curl in spherical polar coordinates, that's quite an expression. But because we only have a phi component, it shortens up a bit. I'm going to put it right here. So so curl of A has 1 over R sine theta d over d theta sine theta A sub phi, which is what we have here. These are all A sub phi's. And then that's in the R hat direction. And when we have 1 over R minus d over dr, R times A sub phi in the theta hat direction. Okay. So yeah, the curl expression simplifies a bit since you only have the phi component of that field. So we're in spherical polar coordinates now. Okay, let's go ahead and erase the outline. Good, so we have to take that operation and I'm just going to write down the answer and point out how we got it. It's actually not that bad. So we get B equals 2/3 R omega sigma mu naught cos theta R hat minus sine theta theta hat. Interestingly, this here is just the z component. So this is z hat if you transform back to Cartesians, okay? This transforms back to z hat in Cartesians. And again, completely what you expect because of the curl of this rotating around the z-axis. We expect, well, it's not implausible. We'll see that the other one has has more than just z hat. But this form here, bring it back up again, R sine theta, remember that's just the distance out from the axis, R sine theta, since R is measured from the origin. So it really is analogous to the rotating bucket, which does have a constant curl in the interior. Okay, good. So, curl of A, 2/3 cos theta R hat sine theta. So yeah, we could call that 2/3 R omega sigma mu naught. Or omega sigma mu naught z hat if we want. So these are for R less than capital R. And as far as the derivatives go, there's no problem at all. We have everything right here. So d over d theta sine theta A sub phi. Okay. We got a sine theta here. So that's gonna, R pulls out derivative 2 sine theta, 2 sine squared theta, 2 sine theta cos theta, divide by one of the sine thetas, there's your cos theta. Okay, so these derivatives, you just have to sit down and do them. And as far as the r greater than radius, we get, and b equals, cut to the chase here, mu naught r to the 4th omega sigma over 3 1 over r cubed 2 cos theta r hat plus sine theta theta hat. Okay. And this one is for r greater than the radius. So we now have our we have all of our fields. We've got the E fields and we have the B fields. And now we can go to calculating these energy densities and these other integrals that we want. Okay. Yeah. So we'll send this one out. And leave this one here. I don't think my numbering is going to match the program that I just had on the board, but can't resist. So next we're going to calculate energy. So energy E field, which we know is a half epsilon naught integral E squared d volume. So we have a half epsilon naught, and then we see that it's 0 inside, so we're going to be integrating from r to infinity, capital R to infinity. Let's see what we have under this integral here. E squared 4 pi epsilon naught squared r squared. And we'll just do it by shells, so 4 pi r squared, 4 pi r squared dr from capital R to infinity. That should give us the electrical component. And we've got epsilon naught over 2 E squared 4 pi squared epsilon naught squared. We've got another 4 pi. This r squared should have actually been to the 4th. So what we're left with, r to infinity 1 over r squared dr. And this integral will be minus 1 over r. And it's the lower boundary, so that just gives us 1 divided by r. So when the dust settles, cancel one of the 4 pi's, we got another 2 there, so we have E squared over 8 pi epsilon naught capital R. So there's our energy from the electrical half of the field. That was the easy one. Let's see. Yeah, good. We'll eventually we will eventually list all of these results together. Okay, so now we need the energy of the B field, but we have two components of the B field, so we have to deal with the inside and the outside. Inside the sphere shouldn't be bad at all. We have 1 over 2 mu naught integral B squared d tau. 1 over 2 mu naught. And then, since we have this form here, we can see that we're just squaring this constant. This is uniform. So it's just 2/3 r omega sigma mu naught. Square the whole thing and then multiply by the volume of a sphere, 4/3 pi radius cubed. So what does that give us? U naught numerator e squared omega squared r. Good. I'm just gonna r cubed. Wait. Oh, I'm gonna substitute the sigma in here as well. So when I do the sigma, I'm going to have the e over 4 pi epsilon naught r squared. Okay, so that'll be 4 powers of r in the denominator and 2, 3, 5 powers of r in the numerator. So we end up with proportionality to r. I'm just going to go ahead and write down what that gives. U naught e squared omega squared capital R 54 times pi. That's a few lines here on my page. Good, so that is inside. So there's an energy density. We already have one here. We have that one. And now we have to use the outside. Now this one was trivial. This one we actually have to do a little more. I should point out, even if we didn't know this identity here, which you can tease out, it's not hard, squaring this would have just given cosine squared plus sine squared equals 1. Okay. Good. So the next one is going to be this part of the field here. Energy the outside, again 1 over 2 mu naught e squared d tau, and this one takes us into polar coordinates. Let me write down what I have here. Put the sigmas in. Oh yeah, not bad. So 1 over 2 mu naught, and then we can of course square all of this stuff, okay? And really this just goes inside, so it's not so bad. We have this, all those constants can come out, mu naught r to the 4th omega sigma over 3, they're being squared. And then inside the integral, we've got the 1 over r cubed. So that's also squared. That's good, of course. Over r to the 6th. Now here's the nice thing with these unit vectors in spherical polar coordinates. They're just unit vectors and they're mutually orthogonal. So when we square this thing, it's no problem at all. We have 4 cosine squared theta plus sine squared theta. That's it. And now we're integrating over the volume from r to infinity. Actually, let me just write that. Yeah, okay, I'm going to write r to infinity. but I'm just gonna write this d tau right here. Of course, this is r squared sine theta dr d theta d phi. There is no phi dependence, that's just gonna give us a factor of 2 pi. The dr is gonna be trivial, or nearly so, and then we'll have to have the sine theta here, cosine squared sine theta, and that's sine cubed theta. So we'll pick up we'll pick up the 2 pi trivially here. The r integral's easy. This one takes a little more work, but it's not that bad. So I'll go straight to what we obtained. There's a few steps there. Actually, there are several lines, but nonetheless, I'll say dot, dot, dot. Okay, nothing fancy there, it's just has to be done. We end up with mu naught omega squared e squared capital R over 108 times pi. Okay, not a number you could have guessed. So now I'm going to gather those together the inside, the outside, get the simplified form for them, and put together all of those results, E and B. Actually, they're all here, right? This one is going to be added to that one. In fact, you see they're very related. This is 54, this is twice that, so they just simplify to a very basic expression. Okay, I can't have everything on the board at once. Let's see what we're gonna leave up. I'll put the total energy up because enough of it is visible. So now the total energy in the fields, which is the electrical plus magnetic. Electrical is 1 over that 8 pi epsilon naught E squared over R that we had. That one was easy. And then this one simplifies to mu naught E squared omega squared R over 36 times pi. Okay. Just common denominator, you got a 3 over 105, 3 over 108, and that's where that comes from. Good, so that's the total energy. So far, so good. So we're going to come back to that. Next, we're going to do, let's see, what do we have on the board? Let's write out the cross product. Okay, we had curl of A is equal to B, so we had B, and we had E. So I want to write out the cross product next. Next, E cross B is equal to because E was 0 inside that sphere, 0 for R less than capital R, and here this is an important one, epsilon naught E over 4 pi epsilon naught R squared. You recognize that. Mu naught R to the 4th omega sigma over 3. Recognize and we had the 1 over r cubed, that went with this one here, sine theta, and then since it's a cross product, it's just the cross product of r hat cross phi hat. Those were our two proportionalities, right? That was a b sub phi and it was an e with the r hat. And this, I'll do a different color, is equal to, oh no, sorry. Theta hat. Sine, it was theta hat. R cross theta hat. Okay. So they're not all here anymore. B was not here. Yeah, I can't point to them right now. R hat, of course, came from the E field. The B field had the R hat and the theta hat. Okay, R hat and the theta hat, and the cross product R hat with itself was 0, and this was left was the theta hat here. That's important. This was a good exercise in spherical polar coordinates because those unit vectors do what they're supposed to do. Actually easier to deal with, or just as easy to deal with. Now, let's remind ourselves, if we are looking at x, y, z, coming in close here, but if we have an r hat like that and a theta hat like that, then if we cross the one into the other, we get phi hat. So that's the right-hand system, r hat, theta hat sweeping down, right, there's theta. And so r hat cross theta hat is equal to phi hat. So that's our E cross B. And remember, the linear momentum was basically going to be an integral over this. Okay? And the integral over your phi hat, when you know, and your volume element is going to vanish. So do I have phi hat here? Yeah, I'll just, I don't have to have it there. So phi hat is equal to minus sine phi cos phi 0. So if you do an integral over this thing with your volume element, the d phi integrals are both going to vanish. D phi integrals are going to vanish. You're not independent of the theta integrals. Okay. So this is why. So the integral E cross B d tau equals 0 because of the direction of that. Which means our linear momentum integral vanishes. So we want to do our angular momentum atom. Okay, I'll send this up. What number was I on? It's the numbers that ended. Okay. So the angular momentum integral, I'll write it down again. There's my E cross B. So L was the integral of R cross epsilon naught E cross B d tau over all of space. And again, E's going to vanish inside, so we're just outside the sphere of radius to infinity. Let's see what I have written down here. Yeah, so we can pull out the epsilon naught. I'll just we've got the, oh, well, the first thing to note, what do we have with the R cross E cross B? E cross B is already phi hat, so we're looking at R hat cross phi hat. So this is going to be proportional to R hat cross phi hat. And R hat cross phi hat is equal to minus theta hat. Again, you want to look at this picture right here, or a similar one, R hat cross phi hat, because theta hat's pointing down, and this R hat cross phi hat's going to be pointing up towards the North Pole, and so it's minus of that theta hat. So the minus theta hat is minus, and this one I'm going to go ahead and write in for us. Do I have it here? I do. So that's minus cos theta cos phi, comma, cos theta sine phi, minus sine theta. And of course the d tau is going to be r squared sine theta dr d theta d phi. So what happens, we're multiplying r squared sine theta to each of these in turn. You can see the d phi integrals are going to make the integrals over this vanish each time. So what we're going to be left with is only the z component. So we only have to do this integral, and we'll be multiplying, this by that, by everything that's in here. Okay. So that will be our L. It'll just be in the z component as expected, right? The thing rotating that way, we expect it to just be in the z direction. So that is satisfying all requirements. And I'm just going to rough in what we're going to have here. Well, I have all of it right now, so it's going to be in z hat direction. I'll put that right in front here. End up with u naught r to the fourth omega sigma epsilon naught over 3. That's that one of them. E over 4 pi epsilon naught. R, I've got r squared and r to the third. I've got my sine squared theta, r squared sine theta, dr d theta d phi. And I'm integrating the whole thing. Phi is 0 to 2 pi, theta is 0 to pi, r is capital R to infinity. So I'm just going to write the r to infinity right here. The other ones are just understood. And we get when the dust settles, u naught e squared omega r pi times 18 z hat. So that is our angular momentum in the field all of space due to that rotating spherical shell of radius capital R. Okay, so we have everything. I want to put these together now that are consult the clock. Yeah, I want to gather all of these results. And I think if I do that, I can erase everything, gather the results on one board, and keep discussing them on the other board. Okay. So we have found everything. We had the energies, actually they're up there, so I'm gonna work with that. And we have the angular momentum. Those are our two goals, and we saw the linear momentum's gonna vanish. So that's what I'm gonna do. I'm gonna gather these results up on that board, and anything else? Pretty sure we have that covered. Okay. Yeah, let's go ahead. Okay, so there's the energy. Let's go ahead and put the angular momentum here in the field once again. U naught E squared omega R pi times 18 Z hat. There's a scalar, there's a vector, and maybe even we'll have our picture here once again. X, Y, Z. The omega refers to that rotational orientation, and the radius here is capital R. Okay, so what we're going to do finally, now that we've found these numbers, these expressions, they're pretty complicated. So the plugging in of the numbers is the worst. Okay, but here's what we're going to do with these two expressions. As mentioned earlier, we're going to compare this to MC squared. So the hypothesis is that, let's number these, 1 and 2. Or the question, let's put it this way. Is all of the mass of the electron actually electromagnetic energy? Okay. So is the electron mass relativistic or how do we want to write that? Can we equate the energy to the relativistic mass formula? Can all of the electromagnetic energy be related to the relativistic formula? We've got the mass energy equivalence. In fact, we'll do relativity later in this semester. So right now we're just putting this W electromagnetic equals m electron speed of light squared. That's the question. And then of course the other question I had said was, can we relate this angular momentum to the spin of the electron? So what we do is we just write down those two equations, and we can then solve for two unknowns. So one of the unknowns is the radius, and the other unknown is omega. Okay, so the formulas are kind of complicated, too many constants in there, but the calculation is reasonably transparent what we have to do. So also L magnitude equal to H bar over 2. Okay. And if we do that, can we find values for omega and R? So we just do that. And this energy can be expressed in an interesting way. 1 over 8 pi epsilon naught r e squared. I'll just write e squared. So you got e squared, and you can factor that. You can factor that out of this expression here. You multiply top and bottom by mu naught epsilon naught. Mu naught epsilon naught. I'm sorry, epsilon naught over epsilon naught, and then in the numerator you'll have mu naught epsilon naught, which is 1 over c squared. So here's what comes out of that. You factor that out and you get 2/9 omega r over c, the quantity squared. So that's the one side of this equals mass of the electron, c squared on the other. And for L equals h bar over 2, that one's actually simpler. So I'll write that one down as well. Yeah. So if we set L equal to h bar over 2, we can solve for omega times r. We'll do that right away. So L equals h bar over 2 immediately gives us omega r is equal to h bar over 2, so we get 9 pi h bar over mu naught e squared. H bar equal to h bar over 2. Cancel 2, you got 9 pi cross multiply mu naught e squared. Good. So those are our two results, or two equations. This one allows us to solve for omega r, because on the right side are all just natural constants and numbers. Plug it in, you get omega r is equal to a pretty enormous number, 9.23 times 10 to the 10 meters per second, an enormous number. In particular, 10 to the 8 meters per second is the speed of light. This is 300 plus times the speed of light. That tells us that this model is not really physically viable, because it would violate all manner of relativistic physics. Okay. So I'll just put as a note here, c is equal to 3 times 10 to the 8 meters per second. But if you take that as a known quantity, okay, so omega r as a known quantity, divide by c, square it, and put it into this equation, then you see, since you're taking that as known, you have r as an unknown. And r can be calculated as well. So using omega r equals this right here, then we can solve for r, and the numerical calculation, which is pretty much every constant we know, we get 2.95 times 10 to the 11 times 10 to the minus 11 meters. Okay, so these are interesting. Couldn't say it's a successful, but success was not going to be had in this endeavor. But it's the kind of exercise that has to be undertaken, and you see how much interesting stuff came into play here. So this is actually not that small. Nuclei, ever since Rutherford, we know our nuclei are about 10 to the minus 14 meters. And so, and atoms are 10 to the minus 10, so this is smaller than an atom, but larger than a nucleus. Okay, nonetheless, glad somebody brought this up because it was definitely on our agenda. It was kind of the major part of our entire chapter 8 work. Good, so we have that, and next time we'll be back into talking about waves. So this is definitely a good exercise. Okay, see you then.